everyone. Today I'm excited to present my project titled Building a Seeing Machine. We are going to explore how to create a radar system using an Arduino and sound waves. This project demonstrates how we can use simple electronics to perceive the world around us, much like a path uses echolocation to navigate in the dark. Let's dive into the details. Building a seeing machine. Step-by-step guide to creating an Arduino-based radar with an electronic sensor. The slide introduces the core concept of a project. We are not just building a toy. We are building a seeing machine. The goal is to create a functional radar system using the Arduino platform. It's a step-by-step journey that integrates mechanical movement, ultrasonic sensing, and digital processing to map the environment without using light. Now, the mission: in the world with sound, radar systems detect objects and measure distance. Our project builds a simple, essential version of this technology. We will use an Arduino microcontroller, an ultrasonic sensor, and a servo motor can an area detect obstacles and display their positions on a screen. The primary mission here is to understand the principle of radar technology. Standard radar uses radio waves. Our version uses sound waves. By combining an Arduino, which acts as the brain, with an ultrasonic sensor and motor, we can perform a 118-degree scan of the surrounding. This allows the system to identify the exact location and distance of any obstacle in its path, effectively seeing through acoustics. The anatomy of the component toolkit: ultrasonic sensor HCSR04, breadboard Arduino Uno, Arduino servo motor, jumper wires, computer for visualizations, USB cable. To bring this project to life, we need a specific toolkit. The Arduino Uno is our microcontroller that coordinates tasks. The SR04 is the ultrasonic sensor that measures distance. The servo motor provides the physical rotation. We use a breadboard jumper with the electrical connections without soldering. Finally, the computer is used both to power the device via USB cable and to run the software that visualizes the radar's output. The ultrasonic sensor: how it perceives depth. The HC/SR04 sensor acts as a system eyes and ears. It works like a path echolocation. 1. Sends a ping It emits a high frequency sound wave to listens for the echo. It waits for the wave to bounce off an object and return. 3. Calculates distance. The Arduino measures the limit delay between the ping and the echo. To calculate the object distance, formula distance time delay times speed of sound divide 2. This is the heart of sensing logic. The sensor has two main parts: a transmitter and the receiver. It sends out a high frequency sound pulse. If there is an object, the sound bounces back. The Arduino records how many microseconds passed during this trip. Since we know the speed of sound is approximately 340 meters per second, we multiply the time by the speed. We divide by 2 because the sound traveled to the object and back. This gives us a very accurate distance measurement. The servo motor, creating the 118 sweep. A radar needs to look in a multiple directions. The servo motor provides the scanning motion, rotating the ultrasonic sensor back and forth in a 118-degree arc. This creates a wide field of vision, allowing the system to monitor a broad area rather than just a single point. To explaining this slide, a static sensor is limited. To create a true radar, we need a sweep motion. The servo motor is perfect for this because it allows for a precise angular control. We program the Arduino to move the servo in 1 degree increments at every single degree. The sensor takes a measurement. This constant movement back and forth across a 118-degree semicircle ensures that no object within the radar's range goes undetected. It transforms a one-dimensional distance sensor into a two-dimensional mapping tool. Now, the system in action. 1. Sweep. The servo moves the sensor to a specific angle. 2. Ping. The sensor sends an ultrasonic pulse. 3. Listen. The sensor waits for the echo. 4. Calculate. The Arduino computes the distance based on the echo timing. 5. Transmit. The Arduino sends the angle and distance data to the computer. 6. Repeat. The cycle continues for the next angle. This slide explains the operational cycle of the software. It is a continuous loop of 6 steps. First, the motor positions the sensor. Second, the pulse is emitted. Third, the system listens for a response. Fourth, the math is done to find the distance. Fifth, This information, both the angle and the distance, is sent to the PC via the serial port. Finally, the loop repeats for the second position. This happens hundreds of times a minute, creating a real-time data stream. Visualizing the data. Visualizing the data, the stream of angle and distance data from the Arduino is meaningless without visualizations. We use a program written in a processing to translate this data into a classic radar interface. The software draws sweeping line and plot a point each detect object, creating a real-time map of the scanned area, decoding the radar screen, distance, angle of detection, the position of the object relative to the center from 0 degree to 118 degree. Data alone is just numbers. To make it useful, we use processing, which is a graphical coding environment. The processing sketch receives the coordinates from the Arduino and draws them on the screen. The green line represents the current scanning angle. When an object is detected, it appears as a red segment. The farther the red line is from the center, the farther the object is. In reality, this interface allows us to see the shape and location of everything in front of the radar instantly. From a hobby project to real-world application. Robotics, navigating obstacles, security, detecting movement in a room, automated systems, measuring level in tanks or bins, assistive technology, helping the visually impaired navigate. While our project is a prototype, the applications are massive in robotics. This is how vacuum robots avoid furniture insecurity. It can trigger alarms when someone enters a zone. In industry, it's used for non-contact level measurement in large tanks. Most importantly, this technology can be miniaturized into wearable device to help blind individuals feel obstacles through haptic feedback or sound, proving that engineering can truly improve lives. Capabilities and constraints. Capabilities and constraints advantage. Low cost and simple to build. Effective for large objects. Limitation, limited range up to 4 meters. Sound absorbing. Materials like a foam are hard to detect and narrow field of view for the sensor itself. To be objective, we must look at the pros and cons. The system is extremely affordable and a great educational tool. However, it has a physical limit since it uses sound. Soft materials like a sponge or thick curtains might absorb the wave instead of reflecting it, making the object invisible to the radar. Also, the HC/SR4 SR04 has a maximum reliable range of about 4 meters. Understanding this constraints is vital for any engineer looking to improve the design in future iterations. Finally, the concludes my presentation on the radio ultrasonics radar. We've seen how sound can be used to map space and how simple components can build complex systems. Thank you for your time and attention.